occurs in vector-valued functions in space. First problem is, I'm going to give you a position vector, r of t is equal to 5t in the I direction, minus 4t in the j direction, and minus 1 over t in the k direction. You want to find the domain. What numbers, if any, can you multiply, can t be? That is, which numbers can you multiply by 5? And the answer is any number. So right now, the domain is any number. We didn't rule out any. For the y, you have to multiply t by negative 4. Well, you can multiply any number by negative 4. We have a starting point 0. We're dividing 1 by t. Then whatever we get, we negate it. We can negate any number as long as it makes sense. You're taking 1 and you're dividing it by things, which we're calling t. You can't divide by 0. That was the only restriction. You can't be 0. You can be bigger than, t can be bigger than 0, t can be less than 0. T cannot be 0. Okay, that problem is done. The domain is t can be all numbers except 0. Suppose that r of t was ln of t, e to the t, and t. Well, so far we'll start off with all numbers. You can only take ln for positive numbers. You can take ln of 0, and you can take ln of negative numbers. So t cannot be the number that crossed off. T so far has to be above 0. You can raise e to any power, to the 0 power, to the positive powers, to the negative powers. And t can be anything, fine. And if you prefer, you can think of it as 1 times t. No matter what t is, you can multiply it by 1 and get an intelligent answer. That is exactly what domains are about. What can their variable be so you get back an intelligent answer? If you take an ln of something, that something has to be bigger than 0. And that was the only constraint. That was the only constraint. T had to be bigger than 0. If you look down here and you look to see what wasn't crossed off, it would be the numbers bigger than 0. That's the domain there. Let us sneak in one more. Suppose you've had that r of t was equal to 2 cosine t 0 and the square root of t. What values can t be? Well, you can take the cosine of any value. You won't get an answer other than between negative 1 and 1, but you can take the cosine of any angle and then multiply that by 2. So far, the domain is all real numbers. 0, well, no matter what t is, the j component will be well defined. It's always 0. And for the k component, you have to be able to take the square root of t. And you can only take square root of t's if t is greater than or equal to 0. That is not negative. And that's your domain. The domain is t is bigger than 0. Should really write domain t is greater than or equal to 0. As long as you take t values 0 or more, you can find r of t. If you can't find r of negative 3, you can do 2 times the cosine of negative 3 You can say the y component is 0, and the k component gives you a hard time because you can't take the square root of negative, I think I said 9, but you can't take the square root of any negative number. What you're taking the square root of must be greater than or equal to 0. You need to keep a running count. For example, if you had 3 over t minus 4, 7 over t minus 6, and 11t plus 1. Well, you can multiply any number by 11 and then add 1 to it. So there won't be problems there. But we have problems with the first two components. We can't divide by 0. That is, when x is 4, or t is 4, bye-bye. And t can't be 6. Else we'll be dividing by 0. So that's what I mean by you have to keep a running count. 4 and then 6. They both have to be excluded. The domain is t cannot be 4, t cannot be 6. It's easier to write down what it couldn't be than what it could be. I mean, you can say it's everything below 4. T is less than 4. Or t is in between 4 and 6. This is how you write t is in between 4 and 6. Or you can be greater than 6. Okay. You can write this. This is an alternative answer. Either write this or write this one, the lower one. Of course, this one is a lot shorter to write. And you didn't have to know that this meant t is less than 4, and this area meant t was between 4 and 6, and that this area t was bigger than 6. You didn't have to know that, but yet you still get full credit. Unless your teacher says you can't write your answer like that. You can't say, oh, t cannot equal 1 or t cannot equal 5. You can't say that. If your teacher says you can't say that, well then trust your teacher. He or she's going to be grading your exam. I want to find the speed. Actually, I want to find r prime of t. I want to find r of t, the magnitude of r of t. R of t is given to be the sinus 3ti plus the cosine 3t in the j direction plus t in the k direction. I, j, and k are vectors. They really should get arrows above them. Well, to find this, it looks like the answer is going to be the square root of 10, but you square the I component. That sine squared 3t, plus you square the j component. Oh, excuse me, square root of 2. That gives you cosine squared 3t. And then you square the 1, and how about, I don't get what I've been saying. What am I thinking? This is 1 plus t squared. That's the magnitude of r of t. So if it's in 3 dimensions, you can handle it. You can handle the magnitude. Square the first component, square the second component, square the third component, add them up, square root the whole thing. Okay, so we're told, it's an interesting problem. We know that r of t is 4 cosine t, 4 sine of t, t over 4. Okay, that we know. And we also know that depending upon the angle we look at this graph in, it looks differently. It might look like that. It might look like that. Might look like that. Okay. Depending upon how you look at this graph, it might just look like a circle. Z, Y, X. Now the question is, how were you looking? You were looking from which point? I will give you 4 points, and I want you to match up which graph that we see to the point, to which of these points. That is, if we're looking at 0, 10, 0, 20, 10, which of those 4 graphs would we see? These are, if you think about it, if you're looking from the z-axis, if you look at all of these, they seem to be a spiral going up, up, and away. So maybe I didn't draw it perfect, but it seems like the spirals all have the same radius. They all have the same radius. Okay, they all have the same radius, whether I drew it that way or not. So if you look from straight above, what you are going to see is a circle. That's what you're going to see. You are going to see a circle. This was looking at it from 0, 0, 20. That is, you're up here. Well, that's not true. You're out here on the Z at 20. And when you look to this, you will see just a circle. And so we dealt with this. Well, where might it be where X is 20, but Y and Z are to 0? Which might that one be? Now, if X is 20, that means we're out here at 20, and we're looking. And basically, this is what we're going to see. We're going to see that graph. That's what we would see. Think about it. You're like on the floor looking kind of up at this spring. And that's what you're going to see. Now, the negative 20, 0, 0 is going to be this one. Negative 20, 0, 0. It's very symmetrical to the one right beneath it. Okay? The only difference is the way that the x-axis is going to be. It's going to be, I guess, out here at negative 20. I just want to be sure I agree with that. Yeah. Okay. And the last one is going to be this one here, and that's where you're basically not on any of the axes. You're looking from a point outside. You're looking from a point far away. Not from directly above, not from the left, but from a point outside. And this is what you're going to see. 10, 20, 10. Suppose you were asked to sketch this. R of t is equal to 2 cosine t to sine t t. So as t changes, z is going to change accordingly. Remember, x is the first component. Y is the second component, and Z is the third component. Now, if you square x and you square y, and you add them up, well then you're going to get this squared, which is 4 cosine squared t plus y squared, which is 4 sine squared t. If you factor out the 4 cosine squared plus sine squared, that's 1. This is 1. Cosine squared t plus sine squared t is 1. And of course 4 times 1 is 4. That is x squared plus y squared is always 4. It's always 4. Regardless of what z is. Z is t. It's always a circle of radius 4. Always. But z goes up and down. So you get circles. Remember, this is just in the xy plane. You have circles in the xy plane that just go up and down. That is, you get a cylinder. You get a cylinder. And since t can be negative, z, which is equal to t, can be negative. Z, y, x. You always have circles of radius 4, whose radius is 2. That's r squared, so r is 2. There's 2. And this circle, this goes higher and lower. And like I said, it also goes lower. In fact, I should point out that it spirals around. Let's see, when t is 0, then t is 0. Sine of t is 0, so cosine is 2. Okay, so sorry, it starts out here, and it just spirals around. It spirals around. but nonetheless it fills up this cylinder. It makes this cylinder. Actually, what's in red is the row graph, sorry. What's in red is the row graph. You can have a very similar one. RT is 2 sine t 2 cosine t e to the negative t. Well, if this is x and this is y, we just learned that x squared plus y squared equals 4. There's no difference between this and the last one, at least what I've done so far. And z is different this time. It's e to the negative t. Now this is always bigger than, it's always bigger than 0. It's not even ever equal to 0. It's always bigger than 0. Negative t can be any number. E to any number is bigger than 0. Okay, so I know that in the xy plane, x squared plus y squared equals 4. But you know what? This point, this circle, won't ever be, because that's when z is 0. But z is never 0. E to the negative t is never 0. But it moves up from there. For example, if t is 0, then z is e to the negative 0, which is e to 0, which is 1. And of course, x squared plus y squared is 4. So you go up to z equals 1. You go up to z is 1, and you draw, you have a circle. You have a circle there. And then when z is bigger, you have another circle. In fact, it's going to be points around this cylinder. Why will it not be the cylinder? Because it doesn't say that z can be, z is not open. Z is not open. Okay? If they just told me that r of t was 2 sine ti plus 2 cosine tj, then they're saying z can be anything. They're saying z can be anything. Well, that's not true. They would say z can be, the z component will be 0, but that's not true. That would just, this would just be the circle in the origin. But our z's can change. X squared plus y squared equals 4 will never change. Z can change. Z is going out. If you know anything about the graph e to the negative t, it looks this way. It looks that way. It can take in all numbers from just above 0 and above. Okay. Now let's see. When t is very, very small, when t is really large, okay? This one grows a bit quicker, but it's something like that. It will have, this is around the surface. This is around the surface of the cylinder. It's around the surface of, say, a soda can. It looks just like that. If they tell you that z is x squared plus y squared, then z can be anything. Z can be anything. They tell you that x squared plus y squared is equal to 4. Actually here z can be anything. In the last one, that wasn't exactly true. What I meant by that is you can pick a value for z, any positive value for z, and figure out x and y. But z here can be anything. So that's going to be a circle of radius 2 in the xy plane, but the height can be whatever you want. And that's exactly when you're going to get, say, like a soda can, a cylinder. X, Y, and Z. There's your cylinder. Okay, so we drew a number of graphs, which is good. Now these are hard to do, but when a sketch the space curve represented by the intersection of the given surfaces. Suppose you know that z is equal to x squared plus y squared. And the other equation is x plus y equals 0. And they wanted to write the equation of the intersection points as a parametric equation where the parameter is x equals t. The parameter is t. They tell you x is t. Okay, let us draw this. For different values of z, we get circles with bigger and bigger radiuses. As z gets bigger, the radius gets bigger. So this is z equals x squared plus y squared. Why is z not negative? Very simple. Because x squared plus y squared can't be negative. And it has to equal z. If x squared plus y squared can't be negative, the right side is never negative, and the left side, which is just z, is never negative. Okay, now the next one. X plus y equals 0. That is y equals negative x, and z can be anything. So y is negative x. For example, if x is 1, then y is negative 1. Which gives you that point right there. And of course, the origin works. Basically, you get that in 3 dimensions. Z can be anything. Z here can be anything. That is, this point, it can go up. This point can go up for a particular amount, actually any amount. It can go up. It can go up. Why? Because, remember, if this x and that y, when I add them, give me 0, and all I do is I go up, which should be vertical, not on the diagonal like I've been drawing, should be up. This point right here, it'll have the same x as down here. It'll have the same y. The x plus y will be 0, like it's supposed to be. And z can be, say, 4 now. So basically, you bring every point up the same amount. And what you get are these points. So basically, you are slicing this bowl. Think of this as a ball, a fruit bowl. You are slicing it with this plane. And the question is, how do you describe the equation? How would you describe this? Well, we can't argue that x is t. They told us that. And we know that y is negative x. It's negative x, but x is t. And the z is equal to x squared plus y squared. That is t squared plus t squared. That is 2t squared. X equals t, y equals negative t, and z equals 2t squared. That describes the surface where they intersect, where this plane intersects the bowl. And usually they'll start you off by saying x equals t or x equals t plus 1. Suppose you have that x squared plus y squared is equal to 4. That's the equation of one surface. And that z is equal to x squared. And the parameter is x is equal to 2 sine t. 2 plus sine t. 2 plus sine t. So first we want to sketch this. Well, x squared plus y squared equals 4. Those are circles of radius 2 in the xy plane. But z can be anything. If you don't see a z, then z can be anything. Well, what that's going to give you is a circle that can be raised and lowered along the z-axis. So if you have this circle, and you can raise it. You can raise it and get a circle higher up. That's exactly what's going to happen. Actually, the original circle is too big. So that's what's going to happen. Z can be anything. So you take this circle on the origin, and all you do is you raise it. You don't change the x and the y values of any of the points, but you change the z. This point can go up 5. This point can go up 5. This point can go up 5. So can this point. And if you were to plot enough of these points, you would see it's going like that. And there's your graph. The circle on top should have been a little bit bigger. But nonetheless, it's a can. Okay, now we want to graph z is equal to x squared. Well, if you just had the x and the z-axis, you'll know that it will look this way. And instead of z, we had y, and I call that y. We know it goes like this. All that happened is it's not y, it's z. I changed the letter. It looks like that. And it has height to it. It has height to it. It can come out of the board. The only thing is, in our diagram, is that the x is coming out of the board. Z is just going straight up. So what we want to do is plot this just in the YZ plane. Excuse me. So in this equation, y can change. I meant to say y can change. So z is equal to x squared. What that graph is going to look like is the following. X and z. Right here, that's where y is 0. That is where y is 0. Now, something is wrong here. I don't want to plot points, but we can do this. Maybe I'll plot points. When x is 1 plus or minus 1, z is 1. So here's 1, here's negative 1. I go up 1. And we know it crosses the origin. So in fact, with these 2 points, 3 points, I think that's enough for me to be able to graph it. There it is. Now what happened is that y can get changed. 1 can change y. And you get something like that. It looks like this distance is longer than that one. But other than that, there it is. And you're slicing them. The question is, what do you cut out? The question is, what do you cut out? And we can describe this parametrically. We know without a doubt that x is 2 plus sine of t. That goes without saying. Okay, so we have x in terms of 2. We know that x squared plus y squared is 4. Bringing over the x squared, we know y squared is 4 minus x squared. Let's work out x squared. It's 4 plus 4 sine t plus sine squared t. 4 minus 4 is 0. So y squared, it's negative 4 sine t plus sine squared t. I suspect that's going to be negative. With a negative in front will make it positive. So y is equal to the square root of negative 4 sine t plus sine squared t. Of course, sine squared t won't be negative, so sine t will. I want to see something. Yeah, I was right the first time, sorry. In the top left corner, it's x is equal to 2 sine t. 2 times sine t. 2 times. Things will definitely work out a lot better now, sorry. So you bring over the y squared, and you bring over the x squared, you get 4 minus x squared. But x squared is 2 squared times sine squared t. This is 4 times 1 minus sine squared t. But 1 minus sine squared t is cosine squared t. Remember, sine squared t plus cosine squared t is 1. Bring this over to the other side is negative sine squared t. And you get 1 minus sine squared t is cosine squared t. That's what y squared is. So y is the square root of 4 times the square root of cosine squared. So now I have y. Now I need to find z. But z is x squared. In the very top I have x, I square it, I now have z. Okay, so the boxed equation, that's my parametric equation. I have x in terms of t, I have y in terms of t, and what do you know? I have z in terms of t. So that's my parametric equation of the points of intersection. I drew it, and I got the equation, the parametric equations of the points of intersection. I described that surface area of intersection by those parametric equations. It's pretty neat. The next set of problems, they're very straightforward. They're limit problems. Generally, you can think of them as three limit problems. Suppose you have ti plus t squared minus 2 about minus 4 over t squared minus 2t. J plus 3t squared k. Basically, this is just three limit. It's three limit problems. It's the limit of the first. Now, whether you write this or not, you must think it. In fact, you could take the limit, times it by I, plus the limit as t goes to 2 of t squared minus 4 over t squared minus 2t. That limit in the j direction plus the limit as t goes to 2 plus 3t squared and times the k vector. Okay, it's just three limit problems. You should always try substituting. That's just 2. When t is 2, t is 2. I plus. When t is 2, the top is 2 squared, which is 4, minus 4, which is 0. And the bottom is 2 squared, which is 4, minus 2 2's, which is 4. 4 minus 4 is 0. So I'm getting 0 over 0. Now you can factor the top as the bottom, or you can invoke L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom. Okay, that limit, then the j direction, plus, plug in 2, 3 times 2 squared is 4. So it's 3 times 4, which is 12. Now you plug in 2, you get 4 on the top. 2 times 2 is 4, minus 2 is 2 on the bottom. 4 over 2 happens to be 2 in their j direction, plus the 12 in their k direction. It's just Calc 1 and Calc 2 limit problems. 3 at a time. 3 at a time. What is space saving? Okay? I get to ask you to do 3 limits and only write limit once. It's just 3 limit problems. If any one of them doesn't exist, then you say the limit doesn't exist. Whereas before, if I gave you 3 limit problems, and the first one was 2, and the second one was 3, and the last one was undefined, that would be your answer. 2, 3, and undefined. But now you would say the whole answer is undefined. Try one more. The limit as t goes to 0 of t squared 3t 1 minus cosine t over t. The limit of the first. 0 squared is 0, comma. The limit of the second. 3 times 0 is 0. Limit of the third. 1 minus cosine is 0. Cosine is 0 is 1. So you get 1 minus 1, which is 0. And then you're dividing by 0. That's the problem. See, you invoke L'Hopital's law. You get 0 over 0. Take the derivative of the top. Take the derivative of the bottom. Dividing by 1, don't even bother. You get the sign of 0, which happens to be 0. So you get the 0 vector. Don't just write down 0. Definitely put a bar above it, or make it bold. Okay? Putting a bar on top is their equivalent to making it bold. So limits, just go back and review your limits. You have my calculus videos. You can go back and look at Calc 1 and Calc 2. You have my other calculus videos. Okay, so we want to know the interval in which this position vector is continuous. Well, if t was any value, I would know what that is. And if t is any value, I can know what 1 less than t is. So far, it'll be continuous everywhere. T is a polynomial, is continuous on the whole domain. T minus 1 is a polynomial, is continuous on the whole number line. Sine inverse of t is only continuous between -1 and 1. Sine inverse of t is continuous on -1, 1. If you were to draw the sine inverse of t, it will be in between here. Negative pi over 2, -1. Positive 1 pi over 2. The graph looks like that. That is the sine inverse. So we need to combine all three. When is t continuous? All real numbers. When is sine inverse of t? Between -1 and 1. When is t minus 1 continuous? Real numbers. We take the intersection. The first That's the number line. The first, I like to put a 0 in for some point of reference. The first one, t, says the number line can be anything. For sine inverse of t, we said it can only be in between -1 and +1, and it can equal both endpoints. And for t minus 1, it was allowed to be anything. Above the black line, above the number line, above this line, which points, if any, have 3 lines above them? The lines happen to be in green. And the answer is every point between -1 and 1 has 3 lines above them. This point has 3 lines above them. It has that line above them, has the first line above it, the second line above it, and the third line above it. This point out here, it only has 2 lines above them. Exactly at 1, it has 3 lines above them. The final answer will be it's continuous. R of t is continuous on -1, 1. R of t is continuous on -1, 1. You had to look at the intersection of the 3 answers. Where is x of t defined? Continuous. Where is z of t continuous? And where is y of t continuous? Take those 3 answers, find the intersection. If one function is only defined between 4 and 5, another function is defined between 20 and 30, I meant to say continuous. One function is continuous between 4 and 5, the second function is only continuous between 10 and 20, and the third one is always continuous. There won't be any points of intersection, because there are no values that are between 4 and 5 and between 10 and 20. And means both. And can be any number. There are no points that can be in here and in here. So there'd be no answer. The function is never continuous. It's discontinuous everywhere. You have that r of t is equal to e to the -t, t squared, and sine of t. Oh, I didn't mean that. The tangent of t. The tangent of t. Well, e to the -t is a continuous function. I drew it a little while ago. It goes like that. I can draw it without lifting my pen. It's continuous. T squared, I can draw that without lifting my pen. Tangent of t, that's the problem one. So the answer is just going to be based on this one. Because the first two, it said r can be any, here, it said that t can be any value to make it continuous. So there's no restrictions from the first two. The last one's going to give me some restriction. Because if you look at the tangent x graph, you remember between -pi/2 and pi/2, it is as continuous as can be. And between pi/2 and 3 pi/2, it is also as continuous as can be. Same between negative 3 pi over 2. It can be continuous. But it's not continuous at pi over 2, at 3 pi over 2, at negative 1 pi over 2, at negative 3 pi over 2. Okay, it's always continuous between, we know it's pi over 2s. Pi over 2, 1 pi over 2, negative 1 pi over 2, 3 pi over 2, pi over 2 to pi over 2. Now the numbers, they're all odd. Negative 3, and they don't skip any. Negative 3, negative 1, 1, 3, 5, 7. They're always odd. Okay, well an odd number is 2n plus 1. And the other odd number is always 2 more. 2n plus 3. That is, you can write the answer down for any value of n. The tan graph is continuous in this interval. It is continuous in this interval. And since the other function, b to the negative t and t squared, was continuous everywhere, this is the only restriction, the only constraint. R of t is continuous on this interval for n equals 0, plus or minus 1, plus or minus 2, etc. Alright, here's a straightforward problem. Suppose you're given R of t and you're asked to find R prime of t, the derivative. The derivative of e to any power is e to that power. And the power, negative t, is negative 1t. The derivative of e to the power is e to the same power times the derivative of that power, which is negative 1. Derivative of 4 is 0. The derivative of 0 is 0. And there it is. Okay, for the next problem, we're going to have this convention. Whenever I write C, that means C1, C2, C3. It's shorthand notation. So if you have the integral of 2ti plus 1j plus 1k dt, what is this equal? Well, this is 3 separate integrals. Again, whether you write it this way or not, it's the integral of 2d dt in the I direction plus the integral of 1 dt in the j direction plus the integral of 1 dt in the k direction. Again, you want to write this, write it. If you don't want to write it, you have to at least think it. The integral of 2t is t squared plus a constant in the j direction. Plus the integral of 1t is t. That's plus a constant, c2. That's in the j direction. plus the integral of 1 dt, again, is t plus a constant, and this is in the k direction. Now, many people would just write it as t squared plus t squared I plus t squared j plus tk plus c1, c2, c3, that is plus c, plus c1i plus c2j plus c3k. But this, I'm just calling that c. Okay, so I won't write those c's anymore. I'll just add the c1 and the c2j and the c3k at the very end. I'll just write plus c. And as defined on the very top, it's one's able to do that. Ti plus 1j minus t to the 3/2 k dt. Well, the integral of 1 over t is ln of the absolute value of t in the I direction, plus the integral of 1 is t in the j direction, minus this integral. You add 1 to a power. If you have a fraction and you want to add 1, think of that 1 as b over b. In addition, if the bottoms are the same, keep them, add the tops. Now ignore that. How do you go from here to there easily? You add the top and the bottom. That gives you a plus b. And whatever on the bottom, it stays that way. Okay? 3 plus 2 is 5. Keep the same denominator. Now you need to divide by 5 over 2. Divide by 5 over 2. And that's in the k direction. Plus c. And that's what that integral is. Remember, the c was because I didn't write plus c1 and plus c2 and plus c3. I wrote it at the very end. So, what if you have that r prime of t is 2tj plus the square root of tk. And that r of 0 is 1i plus 1j. That means plus 0k. Well, if you have r prime, if you integrate, you get r. The integral of this is t squared j. Remember, this is t to the 1/2. To integrate, you add the powers. When you add the top and the bottom, you get 3. Keep the same denominator. And then you divide by 3 over 2. That's r of t, and this was in the k direction. Plus c. Plus c. So we do have an I component now. Remember, this c is c1i plus c2j plus c3k. So we do have an I component. On one hand, using this rule above, I know that r of 0 is 0 squared is 0. So it's 0j, which I won't write. And this gives me 0 again, so it's 0k plus c is c. 0 plus 0 plus c is c, which is 1i plus 1j. That is c1i plus c2j plus c3k is 1i plus 1j. That is c1 is 1. Okay, c1 is 1. c2 is 1. And c3, well, understand that we're adding 0k. c3 is 0. So now I can go back to this equation here and write down what R of t is. It's t squared j plus 2t to the 3/2 over 3k plus c, which is 1i plus 1j plus 0k's. Combining like terms, I just have 1i. How many j's do I have? T squared plus 1. T squared plus 1 j's. And for k's, I just have this one here. 2t to the 3/2 over 3k. That's exactly what R of t equals. We don't have it up to a constant. We have it exactly. So, to integrate, they give you initial condition, you can figure out where some of the constants are. To a definite integral. The integral from 0 to 1 of 8ti plus tj minus 1k dt. So we integrate, this is 3 integrals from 0 to 1. The integral of 8t dt is 4t squared. From 0 to 1 in the I direction, plus the integral of t is t squared over 2 from 0 to 1. This is in the j direction. Minus, let's say minus, the integral of 1 is t from 0 to 1 in the k direction. Well, you plug 1 in, you get 1 squared is 1 times 4 is 4. You plug in 0, 0 squared is 0 times 4 is 4. 4 is 0. 4 minus 0 is 4. So you get 4i. T squared from 0 to 1 is 1 squared minus 0 squared. It's 1. So 4 times that. 4 times 1 is 4. That's where I get 4. Plus, you plug in 1, you get 1 squared over 2, which is a half. Minus, you plug 0 in, you get 0. So we'll just call it a half. Minus, now first you plug 1 in, get 1 minus, then you plug in 0. 1 minus, and this is in the k direction. So what you get is, let me write it down here, 4i plus 1/2 j minus this, which is 1, minus 1k. So you just integrate one by one and you plug in the upper and the lower limits. It's just 3 integrals at once. Take your time. Now for the next one, we want to sketch this. R of t equals to ti plus 3tj on the interval from 0 to 4. Remember, this is x. X is equal to t, and that's y. Y is equal to 3t. But the second line tells me another way of writing t is x. So it's 3x. Y equals 3x. Oh, I know how to draw y equals 3x. Y equals 3x goes that way. Or does it? Possibly goes the other way. If you think about it, when t is 0, x is 0, and y is 3 times 0. They're both 0. And then t gets bigger and bigger, and then when t is 4, y would be 3 times 4 or 12, and x would be t, which is 3. I meant to say 4. So we know which finish is when x is 4 and y is 12. So yes, it's going this direction. In fact, I'm only going to keep the portion of the graph that has t's between 0 and 4. When t goes between 0 and 4, x goes between 0 and 4, and y goes between 0 and 12. There is your graph. Now, what if we wanted to find out how long this is? How long is this vector? Well, this is an easy one because we get a right triangle. This is 4, this is 12. I will scale it down. I'll divide each side by 4. I hate dealing with big numbers. We'll call that z. I know that z squared is 3 squared plus 1 squared. Z squared is 9 plus 1. Z squared is 10. So z is the square root of 10. This z is square root of 10. But when I go back, I have to multiply all sides by 4. And this side here, the side that I'm looking for, will be 4 times the square root of 10. I mean, you could have gone 4 squared plus 12 squared square root. 16 plus 144 is 160, and 160 is 16 times 10, and the square root of 16 is 4, and the square root of 10 I don't know. You can deal with the big numbers. You're going to get the same answer. For me, I'd rather deal with nothing above 10. 160. That scares me. That's a big number, especially the square root of it. Okay, that completes the section, curves and vector value functions in space.